Welcome to the course on plasma physics and applications. Today we will continue our discussion on thermonuclear fusion. We will study the two approaches that are possible on Earth to confine a plasma and satisfy the conditions that are necessary to make a fusion reactor work. These two approaches are the inertial confinement and the magnetic confinement. For inertial, we look at the energy balance, we look at the effect of the pellet compression and the rocket effect. We look at the two possibilities of driving the pellet, direct and indirect drive. We'll also briefly investigate the challenges that physics and engineering poses to this approach. For magnetic confinement, we look at the linear and toroidal devices, their differences and their similarities. We look at the tokamak concept, and we'll briefly illustrate the progress that we are achieving towards a burning plasma. We have calculated together that in order to achieve fusion in a reactor, we need to satisfy two conditions at the same time. We need to have a temperature that's about 10 kV or higher, and we need to have a confinement quality measured by the product of the density times the confinement time of the energy in our plasma that is at least of the order 10 to the 20th per cubic meter times seconds. If we exclude the possibility of confining plasma by gravitation, which is of course impractical on Earth, we have two possibilities. We have the magnetic confinement, which will be based on the use of magnetic fields to trap the charged particles that form a plasma, or the inertial confinement, which is based on the use of small pellets, which will made implode by large energy flux that will be injected on their surfaces. For magnetic confinement, we can reach relatively large confinement times of the order of a second, which implies that the densities that we'll need to satisfy the criterion for fusion will not be too large. In fact, it will be much smaller than the density of the air that we breathe, for example, typically in the order of 10 to the 20 per cubic meter. In the inertial confinement approach, which will be the one we discuss first today, we can only achieve very short confinement times for the energy, let's say of the order of a nanosecond. That implies we need to really reach extremely large densities of the order 10 to the 31st per cubic meter. That's much higher than the density of solid material. Let's start our discussion with the basic principles of inertial confinement fusion. Let's look at the confinement time first. For that, we can consider the time for the ions to fly out of the pellet. We can call that tau I and evaluate it as the size of the pellet, its radius, divided by the typical speed with which the ions will move inside the pellet. That is the speed of sound. Cs is evaluated by the square root of the temperature divided by the ion mass. This is the confinement time for particles. Now we have to compare that to the time that it takes for a certain energy flux to heat the pellet, to look at the heating. In particular, the heating time by a power that's deposited on the pellet surface by an energy flux F. Let's call this time tau H for heating, and let's express it in a formula. The time is given by the energy in the pellet divided by the power deposited on the surface of the pellet. The energy in the pellet is the energy density of the plasma in the pellet times its volume. So we have 3n times the temperature times the volume of a pellet, which you will assume to be of spherical shape, for a third pi r cube, divided by the energy flux F times the surface of the pellet, which is 4 pi r squared. Can simplify the different terms and end up with a simple expression, which is n times T times the size or radius of the pellet divided by the energy flux F. Obviously, we need to have a heating time that's shorter than the confinement time. So the condition is that tau H be smaller than tau I. Let's translate into a formula for, in particular, into a condition for the energy flux F. So let's write NTR over F smaller than the confinement time, r over the square root of T over mi, and express this in terms of f, which therefore needs to be larger than nt times the square root of T over mi. And we note that in this condition the size of the pellet does not enter anymore. I remind you that here I have assumed no compression effects, just heating on the surface of the pellet by an energy flux F. Let's take a numerical example. Typically we consider a temperature for fusion of about 10 keV. Let's take the density of solid deuterium for N. If I put the numbers, this gives me a value of F that needs to be larger than about 5 times 10 to the 19th watts per square meters, which is of course a very large value. The hope to achieve that is only perhaps via lasers or heavy ion beams. Having seen the basic principles for inertial confinement, we are now ready to evaluate the energy balance. We have a laser characterized by a certain energy, EL, that is injected onto a pellet. There will be a certain efficiency with which the laser energy will be transformed into the pellet thermal content. So the thermal energy in the pellet will be equal to the laser energy times this efficiency, which we can call epsilon c. This will lead to heating and hopefully fusion energy production. So the pellet will therefore produce an energy EF via the fusion reactions that will happen in its core. This fusion energy EF is used to create electricity for energy production. Let's call the energy for electricity E sub E. And of course in this process there's a finite efficiency as well. Let's call that epsilon thermal, epsilon sub TH. E sub E will be equal to the fusion energy times epsilon TH. Of course this EE will give energy production for the outside world, if you like. But also part of it will be used to drive the laser. So the laser energy will be equal to a certain conversion efficiency, which we can call epsilon sub L, times the electrical energy that will be used to drive it. Now, of course, not all fusion energy will be used to create electrical energy because of the final conversion efficiency, and not all electrical energy will be used to drive the laser. We'll only have a fraction of it in principle. There will be EE times a factor which we can call F recirc, which is the fraction of energy that is recirculated to run the reactor, mostly for plasma heating. So we now have the complete loop for our energy balance, and we can evaluate what the different conditions are in practical situations for a fusion reactor. Here we see the same loop drawn in a more schematic way. And what we do is that we develop the relations between the different steps. In this situation, we consider the worst case scenario, that is, we recirculate 100% of the power or the energy. We need to express the pellet size as a function of V thermal, therefore as a function of the laser energy. We consider our usual temperature for fusion of about 10 keV and the relevant value of the fusion cross-section times the velocity for the DT reaction. And you've introduced a reference value N0 for the density, which is the density of solid deuterium, and the confinement time for the ions that we have calculated before. We have a very compact expression that relates the densities in the pellet to the laser energy that is required to satisfy our criterion, and the efficiencies of the different steps that we have discussed. This expression is numerically correct if we consider the energy in megajoule. Using this expression now we can put some numbers and evaluate the driver energy that's needed for a situation in which we consider the density N equal to N0, that is the density of solid deuterium. We consider the efficiency epsilon c to be about 10%, the efficiency epsilon L to be about 5%. That's the efficiency with which the electricity is translated into laser power. And the efficiency epsilon thermal, which is the efficiency of the transformation of fusion power into electricity of about 40%. The number we reach for the laser energy, for the driver energy in general, is very, very large. It's 10 to the 15 joules. That's about 50 times the Hiroshima bomb, and if we consider that the pellet size will be of the order of a few millimeters, that's really a very large number. And in fact, it's orders of magnitude more than we can achieve in the laser pulses today, which is about 2-3 megajoules. To reduce this value of the needed laser energy, we must increase the efficiencies, but we also must increase the ratio n over n0, that is, we must compress the pellet. So let's take slightly more optimistic numbers, an efficiency epsilon c of 20%, an efficiency of epsilon L of about 8%. We keep epsilon thermal to about 40%. And we do the exercise the other way around. So we impose that EL be 2 megajoule, which is what we can achieve today. What do we need for n? Well, we reach a value of n that must be about 3,000 times n0. So the density must be 3,000 times the density of solid deuterium. That means we have to achieve a pressure that is 3,000 times n0 times the temperature. And if we put in the numbers, that corresponds to about 2 times 10 to the 17 newtons per square meter, which again is a gigantic pressure. If we consider the laser pressure, that is the pressure generated from the laser beam given a certain energy flux F for the most powerful laser beams we can create today, and that is calculated simply by dividing the energy flux F by the speed of light, that's about 5 orders of magnitude smaller. So we're really far away from what we need to achieve to satisfy the condition for the pellet to fuse. So the question is how to boost this pressure. Here's a simple idea. We can generate an implosion by ablating matter at the pellet surface. So if we have our pellet, we have a layer at the edge of it, which can be ablated, for example, by launching onto it a very large amount of energy. By rocket effect, that is by conservation of momentum, there will be an inward motion of the first layers inside the ablated matter. This is the rocket effect. The pressure that results can be calculated with a very simple model. Let's call this P rocket. The pressure is equal to the variation of the momentum, mv, with time, divided by the surface. We assume that v can be considered constant, so the momentum varies because the mass varies, not because the velocity varies. So that's equal to v dm dt over the surface that we would call S. We'll consider the energy flux F, that is the power divided by the surface. The power is the variation in time of the energy, which is the kinetic energy of the matter in the pellet, divided by surface S. Again, we consider that the velocity can be assumed to be roughly constant. So I take 1/2 v square out of the derivative, and we have 1/2 v square over S times the variation of mass with time. That gives me a variation of mass with time dm dt, that's equal to 2sf divided by v square. That I can use in the expression for the rocket effect pressure, or P rocket, which is given by v over s times dm dt. So that is v over s times 2sf over v square. The surface of the pellet cancels out, and I'm left, simplifying also v square with v, I'm left with just 2f over v. So we can now compare what we have achieved in terms of pressure by this rocket effect and the pressure that comes simply from the light impinging on the surface, which we called P laser before. Let's take the ratio of the two, and that is 2f over v times c over f. So for the same energy flux F, we have a ratio that's 2 times the ratio of the speed of light divided by the velocity of the motion of the particles at the pellet surface. So that is, of course, much, much bigger than 1, as the velocity is much smaller than c. So that's how we boost the pressure in the pellet by this rocket effect idea. There are a few additional effects that we need to consider. 2 that are positive, that is, they help us achieving higher pressure and higher temperatures in the core, and 2 that are a little bit difficult to deal with. First of all, the pressure from the rocket effect is helped by the inward propagation of the shock wave that is produced at the first surface, assuming that this shock wave really goes towards the center in a symmetric way. Second, as the core is heated, fusion reactions will start, and the alpha heating that is a consequence of the fusion reactions will start to help as well. However, for this to work, we need to make sure that the pellet size be larger than the collision mean free path for the alphas inside it. So we need a pellet size that's of the order of a few millimeters at least. The other 2 effects are a little bit more difficult to deal with, and they're not helping us. First, we have instabilities in the interaction between the laser and the plasma, and these impose a limit to the laser intensity. Second, the density itself cannot be too high, otherwise the laser beam will be reflected by the plasma frequency cutoff that we have learned about in previous classes, omega p. We're ready now to summarize the sequence of events in inertial fusion. First of all, we have what we call the radiation phase. The laser beam hits the surface and forms a plasma. The second phase is a blow-off phase, which is this rocket effect that we have discovered together. The surface material is blown off, and by conservation momentum, the rest is pushed towards the center. The third phase is therefore the implosion phase, and with implosion comes the compression of the core to very high density. And the fourth phase, if everything works fine, is the thermonuclear burn of the compressed fuel. Let us now briefly discuss the challenges that physics poses to this approach. First of all, the core must not be heated before the shock wave arrives and compresses it. That implies that design of the pellet needs to be really carefully done. It also implies that the timing of the laser pulse is very delicate. Second, there is the question of the hydrodynamical stability of the pellet itself. That imposes very high degree of symmetry in the pellet, as well as in the drive. Therefore, in practice, a very, very delicate question of aligning the beams onto the pellet. The simulation shown here indicates a mixing from the core material that is formed by the DT fuel and the outer material due to a so-called Rayleigh-Taylor instability. 2 approaches are taken to drive the pellet: direct and indirect drive. The direct drive is shown here on the left. This is the simpler of the 2 conceptually. We really have just the pellet on which we inject in an asymmetric fashion as possible all the laser beams. The pellet construction is relatively complicated. There's an ablator of low density around. There's a solid or liquid fuel, and there's a gas at the vapor pressure of the solid or the liquid fuel. The pellet size here shown compared to a human eye is of the order of millimeters. This is the direct drive. The second option is a clever idea that came about to actually lower the requirements on the symmetry of the laser injections onto the pellet, and that's the so-called indirect drive. The idea is the following. Instead of just having the laser beams impinging on the pellet itself, we have a very small little chamber around it called a hole-around, bigger than the pellet itself, of course, but still a relatively small size of a centimeter or so. This is the image of one version, again, compared to a human eye. What does this hologram do? Well, it receives the laser beams through 2 holes. It acts as a black body radiator of X-rays, because the laser beams are so powerful that by hitting the surfaces of this hologram inside, which are made typically of a high-Z material like gold, these surfaces emit X-rays, and the advantage is that this X-ray bath in which the pellet is embedded is more symmetric than the injection of the lasers themselves. So the concept reduces the conditions on the symmetry for the beams. The image shown in this slide is that of the National Ignition Facility, which is the largest operating experiment on inertial fusion, and that's located at the Lawrence Livermore Laboratory in California, US. And shows you how big the facility of this kind is. This system has 192 lasers for a record energy in a pulse of about 2 megajoule and a power of about 500 terawatt. These are lasers in the UV region at 352 nanometers of wavelength. You see in this picture all the amplifiers for the lasers. You see the beam steering optics here, which is of the order of 300 meters of length. And at the end you see the vacuum chamber, which contains the pellet, which is kept in place by a special positioning system, and of course occupies a very, very small volume of the vacuum chamber at the end. Let us now discuss a few of the engineering challenges that this approach entails. First of all, we need to address the question of the efficiency, cost, and reliability of the high-energy driver, for example, the lasers. Second, we need to solve the question of the materials for the first wall of the vacuum chamber. Third, and this is one of perhaps the most difficult ones, we need to address the issue of complexity and therefore cost of the capsule, the pellet itself, and the whole RAM in case of the indirect drive. At present, these elements cost orders of magnitude more than that would need to cost if we wanted the reactor to be economical. And last but not least is the issue of going from a single to repetitive pulses. A reactor will need to operate at a few hertz of a pulse rate in order to be economical and produce power. Having seen some of the problems of inertial confinement and some of the elements of the spacing principles, we're now ready to move to the second approach that we can have on Earth to get a plasma confined in a given region and therefore produce a fusion reactor. That is the approach of magnetic confinement, based on the fact that the plasma is made by charged particles, ions and electrons, and they are subject to electromagnetic force, and in particular they tend to rotate, gyrate around magnetic field lines. This approach allows us to have confinement times that are macroscopic, of the order of seconds, which means that we can afford densities that are relatively low, the order 10 to the 20 per cubic meters, much lower than the density of the air that we breathe. As illustrated in this little movie, this approach is based on a very simple principle, that is, the charged particles that make up the plasma are subject to the electromagnetic forces, in particular to the magnetic force that holds them to the magnetic field lines in their gyro motion around them. Without field, of course, the particles will hit the wall of our reactor immediately and get lost, and the plasma will disappear. With the field, they will be contained in a volume for enough time. The idea of magnetic confinement was declined since the early times into different kinds of schemes. First of all came the linear devices, in which the plasma was confined around magnetic field lines produced in linear configurations. But of course, in this situation, you would have a problem with the two ends of the device itself. So early enough, of course, came also the idea of having a plasma made into a toroidal configuration. This toroidal configuration can take different forms and different details in its concept. We look at a very simple approach next. So let's take a simple toroidal field. Simple toroidal field implies, if we close it in a toroidal machine, implies that there is a certain curvature of the field lines, and there is also a certain gradient of the intensity of the field. These two things lead to drifts, as you have learned in the first part of the course, that separate positive and negative charges. In this example, we have the positive charges on the top and the negative charges at the bottom. When you separate charges, of course, you create an electric field, E, and that will act together with the ambient magnetic field, which is toroidal in this case. We combine with that to create an E-cross-B drift that to take all the plasma out, irrespective of the charges of the particles that compose it. So very, very soon we will lose the plasma to the outside in a purely toroidal device. The idea, therefore, is to avoid charge separation by imposing a poloidal field, so that the particles can sample in their motion regions with opposite drifts and on average have no net drift. In the case of a tokamak configuration, the poloidal field is produced by a plasma current, which is this JT. However, another relatively minor problem arises. This plasma current going around toroidally is subject to the so-called hoop force, which tends to move the current filaments, that is the plasma itself, all the way outside on both sides, on all the sides in fact. How to avoid the hoop force? To avoid the hoop force, or to counterbalance it, we add a vertical field, indicated here as BZ in green. And with the presence of BZ, this hoop force can be actually counterbalanced completely. Here we summarize the different elements of this tokamak concept. We have the toroidal field coils in blue. They generate a toroidal magnetic field. We have a plasma current here in green, which generates a poloidal magnetic field. Therefore, the sum of the two will give a helical magnetic field around, so that particles will experience inward and outward drifts, and on average experience in fact no net drift and be confined. And in addition, we have a so-called outer poloidal field coils that produce a vertical field to counteract the hoop force, and also can produce field for plasma positioning and shaping. One thing we still need to clarify is how to drive a current in the plasma. Well, that's the idea of the tokamak, one of the ideas of tokamak, and that is to use a transformer in which the plasma acts as a secondary circuit, the primary circuit being a coil that's inside the core of the tokamak. If we swing the flux in this coil by changing the current in the coils, of course, we can induce, by Faraday's law, a current in the plasma, which again in turn will produce the poloidal field that we need. And this little movie summarizes what we have just said. Here are the set of the toroidal field coils producing a toroidal field. Poloidal field is produced by the plasma current created by transformer action, and the helical field then traps particles as illustrated by having them go around the torus in, out, in, out. An additional set of coils will produce the vertical field to counteract the hoop force and to shape the plasma. The picture with which we end this movie is that of the largest tokamak existing so far, that is the jet tokamak in Europe, in England, close to Oxford. The progress in magnetic confinement fusion using the tokamak concept primarily has been fantastic. If you look at this progress in terms of the temperature achieved for the plasma, here illustrated on the vertical axis, as a function of what I call here the fusion performance, which is the product of the density times the confinement time, our famous N times tau E, times the temperature, we see that the different generations have really made significant jumps into this graph. The tokamak concept was developed in the 60s. Very soon, in the 70s, we reached temperatures of the order of 50 or even 100 millions of degrees. So temperatures that are already taking us in the fusion conditions for that part. What was still to be done, and somewhat still to be done, is to obtain those temperatures at very large values of confinement times and densities. The second generation in the 80s made a significant jump, not so much in temperature, but again in density and confinement time. And the third generation, with which we achieved almost break-even, typically in two machines and American machine TFDR and in the European machine JET, which we have just seen, and of which a picture is actually reproduced on this graph. These break-even conditions were approached by having very significant increases in confinement time. What we still need to do is to make the jump from Q slightly lower than 1, where Q is the fusion gain, again, fusion power divided by input power, into the regime of a burning plasma with Q larger than 5. And that's where we intend to do with the ITER project, which aims at obtaining about 10 for Q, and of course for the reactor, values of capital Q that are in the range of 30 to 40. Let us say a few words about ITER, which will be the first burning plasma. You see here the construction site for ITER, which is located in the south of France at Cadarache. ITER is a result of a very large international collaboration involving several partners, representing, we say, about 80% of the world population. You see here the pit in which the tokamak will be constructed, and you see on the right the layout of the tokamak itself with all the systems we have discussed today, and of course much more ancillaries to make the system work overall. You also notice the size of the plant as compared to the typical size of a human person here. ITER will be aiming at providing a fusion gain, capital Q, of 10 or more, a fusion power of about half a gigawatt for a duration of several hundreds of seconds. It will therefore be the first demonstration of the scientific and technological feasibility of fusion and of its safety. We can now summarize the lecture. We have seen today we have two approaches on Earth to reach the conditions that are necessary for a fusion reactor to work: inertial and magnetic. For inertial confinement, we have seen that the efficiency of the driver and of its conversion to pellet energy and heating are crucial. The implosion of the pellet can be helped by the rocket effect. We have seen that the indirect drive can help improving the symmetry of the implosion. We have also noticed that there are challenges on the physics side and on the engineering side. On the physics side, the heating of the core and the stability of the pellet are the most important ones. On the engineering side, we need to really address the issue of the cost of the pellet and now the repetition rate of the pulses. We have introduced the concept of magnetic confinement based on magnetic fields to hold the plasma together in a cleverly designed cage. We have seen that toroidal devices are needed for this cage to be efficient. And we have mentioned and briefly introduced the ITER project, which will be the one that will provide us with burning plasmas, and therefore the one that will demonstrate the fusion is feasible both scientifically and technologically, and that it is safe. In terms of magnetic confinement, we did not go into much depth because we will concentrate on it in several lectures in the rest of this course.